Have you ever really thought about the invisible forces that are right now powering pretty much everything around you? We know electricity and magnetism are connected, right? They're like two sides of the same coin. But for the longest time, we only understood half of that relationship. So back in the 1820s, scientists had this huge breakthrough. They figured out that an electric current could actually create a magnetic field. It was a total game changer. But it left this massive nagging question hanging in the air. If electricity can make magnetism, can magnetism make electricity? And I mean, the biggest names in science at the time, people like Michael Faraday over in England and Joseph Henry in the US, they were obsessed with this. It just felt like there had to be some kind of symmetry, a way to complete the circle. But for years, the answer was just missing. And let's be clear, this wasn't just some academic puzzle. Figuring this out was going to completely change the world. It was the key to unlocking a technological revolution. The answer, when it finally arrived in 1831, didn't come from some giant, complicated machine. Nope. It came from a bunch of incredibly simple, just brilliant experiments done by Michael Faraday. He was about to pull back the curtain on one of nature's biggest secrets. So let's actually walk through what Faraday saw, because the real genius here is in just how simple and elegant his observations were. Okay, so what did Faraday actually do? He had a basic coil of wire and a bar magnet, and he just moved the magnet toward the coil. And boom, a current appeared out of nowhere. Then he pulled the magnet away, and the current popped up again, but flowing the other way. And get this, the faster he moved it, the stronger the current got. It didn't even matter if he moved the magnet or the coil. As long as something was moving relative to the other, he got electricity. But the second he stopped, poof, the current was gone. And that was the key, the absolute eureka moment. It wasn't the magnet itself that was creating the electricity, it was the change. The secret ingredient was motion. The amount of magnetic field passing through that coil had to be changing for anything to happen. That was it. Now, these incredible observations didn't stay as just observations for long. They were quickly turned into a couple of really elegant laws of physics. Laws that, today, run everything from power stations to the charger for your phone. So, first up is Faraday's law. This is the how much law. It tells us exactly how much voltage, or what we call electromotive force, you're going to get. And it's beautifully simple. The faster you change that magnetic field passing through the coil, the more voltage you create. It's basically the law of more change equals more power. Okay, so that's one piece of the puzzle. We know how to figure out the amount of current. But what about its direction? Why did it flow one way when the magnet got closer, but the opposite way when it moved away? Well, for that, we need Lenz's law. And you can just think of this as nature's grumpy, contrarian law. It basically says that the current will always flow in a direction that tries to cancel out whatever change you're making. It's like nature's always saying, nope, don't like that. Let's put it back how it was. Think about it like this. You try to push the north pole of a magnet into a coil. The coil immediately generates its own current, which in turn creates its own magnetic field, with a north pole pointing right back at you, trying to push your magnet away. It literally fights back to keep the status quo. It opposes the change. And this opposition isn't just some subtle little force. It can be incredibly powerful. A great example is the jumping ring experiment. You just place a metal ring over a big coil, then you flip a switch that sends a huge current through the coil, creating a massive magnetic field that shoots upward through the ring. Instantly, the ring creates its own opposing magnetic field. The two fields repel each other so violently that the ring is launched feet into the air. It's a perfect, dramatic example of Lenz's law in action. So we've got these really cool laws of physics, but what's the big deal? Well, as it turns out, the big deal is pretty much everything. This is where we see how these simple ideas built our entire civilization. Because those two simple rules we just talked about, Faraday's law and Lenz's law, they are the beating heart of two devices that our modern world absolutely cannot live without: the electric generator and the transformer. A generator is really just Faraday's original experiment, but on a massive scale and put on repeat. You use some force, wind, water, steam, whatever, to spin a giant coil of wire inside a powerful magnetic field. As it spins, that magnetic flux is constantly changing, which, thanks to Faraday, induces a continuous voltage. And that continuous spinning is what gives us the smooth, oscillating, alternating current, AC power that comes out of every outlet. And then you've got transformers, the real unsung heroes of our power grid. They use induction to change voltage levels. A power plant will use a step-up transformer to crank the voltage way up so it can be sent over long distances efficiently. Then, right near your house, a step-down transformer on a pole or in a box brings that voltage way down to a safe level for your toaster and your phone charger. It's a genius system, all based on induction. But there's an even deeper, almost philosophical idea going on here. When we're making all this happen, we're not just pushing electrons around. We're actually storing energy in the empty space of the magnetic field itself. The concept is called self-inductance. See, a coil doesn't just fight against outside magnetic fields. It fights against changes in its own current. If you try to start a current, the coil pushes back. If you try to stop it, it tries to keep it going. The absolute best way to think about this is as electrical inertia. And this is where things get really, really cool. Just look at the math. The energy of a moving object, its kinetic energy, is 1/2 times its mass times its velocity squared. Now look at the energy stored in a magnetic field. It's 1/2 times its inductance times the current squared. The equations are practically identical. Inductance is to electricity what mass is to motion. It is a fundamental resistance to change. And the implication there is just mind-blowing. It means all the work you do fighting against that electrical inertia doesn't just vanish. It gets poured into and stored within the magnetic field that's filling the space around the wire. A magnetic field isn't just an area of influence. It's a physical container for energy. So let's bring it all home. What are the big takeaways here? First, it's all about change. A magnet sitting still does nothing. A changing magnetic field is the secret to creating electricity. Second, nature pushes back. Lenz's law shows us that systems fundamentally resist change, which is a core principle of stability. And finally, all of this, the single, simple discovery, is the invisible engine that powers our entire modern world. Learning to harness electromagnetic induction was this incredible moment where we as a species learned to command an invisible force of nature and remake the world with it. And it just makes you wonder, doesn't it? What other invisible forces are out there, just waiting for their own Michael Faraday to come along and figure them out?